The performance of a building is influenced by a complex interplay of physical processes. Among these, the HAM Triad, heat, air and moisture, stands as a foundational concept in building physics. By understanding how these three components interact, architects and engineers can design structures that are not only energy efficient, but also comfortable, durable and sustainable. The HAM Triad refers to three key processes that shape how buildings behave. First of all, we have heat. This component deals with the transfer, storage, and loss or gain of thermal energy. It encompasses conduction through materials, convection via air movements, and radiation between surfaces. Then we have air. Air movement, including infiltration, exfiltration, and ventilation, is a critical factor in determining indoor air quality and energy efficiency of a building. The flow of air affects how heat is distributed and how moisture is carried into and out of the building. And last for this triad, we have moisture. Moisture transfer involves the movement of water vapor and sometimes liquid water through building materials. It plays a significant role in phenomena such as condensation, drying, and the overall long-term durability of a building. Together, these three processes create a dynamic system that directly affects thermal comfort, energy efficiency, and the durability of buildings. Now let's take a closer look at each one. Heat transfer is central to maintaining indoor comfort. In a building, heat is continuously transferred through conduction, convection, and radiation. Conduction refers to the movement of thermal energy through solid materials like walls or roofs, with the thermal conductivity of these materials determining how fast heat is lost or gained. Convection occurs when heat is transferred through the movement of air, whether through natural convection, driven by temperature differences, or forced convection from mechanical systems, both of which play a key role in regulating indoor temperatures. Radiation involves the emission and absorption of infrared energy between surfaces, and properly managing radiative heat can help reduce unwanted solar gains or heat losses through windows or other transparent elements. Air movement within and through a building is often invisible, but plays a crucial role in both comfort and energy performance. Infiltration and exfiltration occur when air leaks through gaps, cracks, or joints, leading to significant energy losses. A tight building envelope helps minimize these losses and helps prevent moisture-rich air from infiltrating into the building. Ventilation is essential for maintaining indoor air quality by providing fresh air for occupants and removing excess heat and moisture. The stack effect, a natural tendency for warm air to rise and create pressure differences, drives airflow through a building. While this effect can be harnessed for passive ventilation, it must be controlled to prevent discomfort or energy waste. Effective air management relies on careful building envelope design, sealing techniques, and the integration of mechanical ventilation systems when needed. Moisture transfer plays a crucial role in building design. While a certain level of moisture is necessary for a healthy indoor environment, excess moisture can lead to issues such as mold growth, material degradation, and reduced thermal performance. Moisture dynamics in buildings are influenced by diffusion, airflow, and condensation. Diffusion occurs when water vapor moves through porous materials, with the rate of movement depending on the vapor permeability of the materials used. Airflow also carries moisture, making strategies for managing air movement essential for moisture control. Condensation happens when warm, moist air comes into contact with a cooler surface, which can be mitigated through proper thermal bridging, insulation, and ventilation. Monitoring and controlling moisture is essential, as even small amounts of condensation can compromise insulation, cause structural damage, and pose health risks to occupants. While each component of the HAM Triad, heat, air, and moisture, can be studied in isolation, their true impact emerges from their interactions. For example, in terms of thermal comfort, a building with excellent insulation, which reduces heat loss, might still be uncomfortable if air leakage allows cold drafts. Similarly, high humidity from uncontrolled moisture can affect both thermal comfort and air quality. For energy efficiency, effective control of heat transfer reduces energy consumption. But poor air sealing can counteract these benefits by allowing unwanted air exchange. And for durability, moisture that penetrates the building envelope can lead to material decay. When combined with fluctuating temperatures, it can cause repeated cycles of expansion and contraction, accelerating structural deterioration. In modern building design, integrated simulation tools, often referred to as HAM tools, are used to analyze these interactions. Such tools allow professionals to predict how changes in one part of the system might affect the whole building's performance. Understanding the HAM Triad is essential for energy modeling, as accurate simulations predicting heating and cooling loads must incorporate all three components to reflect real-world conditions. It also plays a crucial role in sustainable design, where designers optimize building envelopes to reduce reliance on mechanical systems and lower carbon footprints. In moisture management, a deep understanding of moisture dynamics informs strategies to prevent condensation and mold, such as using vapor barriers and ensuring proper ventilation. Additionally, when retrofitting or renovating older buildings, applying HAM principles could enhance energy efficiency and occupant comfort without requiring complete overhauls. Stay informed, stay inspired. TimberTalk.